Suppose there is an electric field that depends on x, y, z, and t, where t is time and x, y, and z are the Cartesian coordinates. This means that for a given choice of x, y, z, and t, there is a corresponding electric field vector. So, for example, I could draw an electric field vector in this orientation at an arbitrary point 1, 2, 5, 0. I could also draw another vector at 1, 2, 6, 0. So as you can see, at a given time, you can draw a bunch of electric field vectors. But what happens as the time changes? So as the time changes, that last number is altered. So say that number now is 1. Then the electric field vectors may have changed to a different location. Maybe here. So that's how you can visualize an electric field that depends on space and time. So we've established that an electric field can change with respect to a parameter t. The electric field can change with respect to time. So we're allowed to take the time derivative of the electric field. It's a partial derivative because the parameters in parentheses include more variables than just the time t. All right, so I'm going to erase the electric field vectors and move this time derivative over to the right. And I'm actually going to multiply this derivative by a constant called the permittivity of free space. So this is the permittivity of free space. Now, in the context of Ampere's law with Maxwell's addition, this term is what Maxwell contributed to Ampere's law. Next, let's add something called the electric current density, which has this symbol, J. The units of this, or the dimensions, are current per unit area. Current per area. All right. What's next in our construction of Ampere's law with Maxwell's addition? Well, we need to multiply this entire sum by a constant called the permeability of free space. So let's do that. Mu naught is the permeability of free space. It's a constant. And the remaining step is to relate this quantity to the magnetic field. So let's do that. I'm going to move this expression over to the right to make room for the magnetic field. It is actually, this expression on the right is actually equal to the del operator cross B, where B is the magnetic field, and this is the del operator. Recall that the del operator can be written like this if you're using Cartesian coordinates. So this is a unit vector in the x direction multiplied by the partial derivative with respect to x plus a unit vector in the y direction times the partial derivative with respect to y plus a unit vector in the z direction multiplied by a partial derivative with respect to z. Sometimes you'll see the del operator written in a compact form like this. Sort of like the components of a vector. So this concludes my video about Ampere's law with Maxwell's addition, and I hope it helped you understand what this equation means.